Right, and the chi-square test is a test for independence, and it's also a test for agreement. Basically, if they agree, they're not independent, and it's just a different way to look at it. But this one we're going to do this is a test for goodness of fit, and it's how well one distribution agrees with another. And goodness of fit is, first thing we're going to do is flip coins in the computer. So get the file, the chi-square file, and go down a little ways and pick a spot, and we're going to flip coins. And I'm going to label this list 1 through whatever. And these are going to be however many coin flips we have. And this is just, I'll extend that, make it 25. So we're going to flip a coin 25 times. And then check and see whether the random number generator actually flips coins fairly or not. I've got the list 1 through 25, and it's purely so that I can have a count. And in that first cell, put rand between 1 and 2. So this is simply going to generate 1s and 2s at random. It could be 0s, 1s, whatever. 1's going to be heads, 2's going to be tails. Right, and this is just one more Excel thing. You'd be a little better at Excel. A lot of times random numbers are useful. Just going to copy that down to 25. 1 is heads, 2's tails. Copy that list of numbers. Do copy, then go right next to it, just so we still have 1 through 25, and we want paste special, and we want to paste values. And the only reason to do this is now we have a static setup of coin flips. Every time you put an entry in, this first column will change. We don't need that. We've got our numbers. So now we need a histogram of 1s and 2s. How many 1s and 2s are there in this? And we can do this a variety of ways. This is going to be our bins, 1 and 2. And for this one, we're going to use a different command that will give a histogram, and that's in the Data Analysis Tool Pack. Have you still got Data Analysis Tool Pack? If you don't, go to File, Options, Add-ins, and there at the bottom it says Go, and the Data Analysis Tool Pack will come up and you just check it. So there's the check. Okay, so we got data analysis. Data analysis tool pack. Go to histogram on the data analysis tool pack. This is another way to make a frequency distribution. It's a little more freehand. Click OK. The input range for our histogram is our static numbers. Our list of coin flips that doesn't change. Whoop, I just changed something. Nope, got it. The bin range is here. The 1 and 2. And here's where you have more freedom to move things. You can put in a separate output range. It doesn't have to be near our bins at all. But we need an output range. I'm just going to put it somewhere. And when you click OK, it gives you the frequency and the bins, so that otherwise we would have had to do frequency here, and it would have put it right next to it, just the frequencies. 12 heads, 13 tails. If I flip coins, what's it supposed to be? 50-50. So out of 25, how many should be heads out of 25? 12 and a half. Okay, so 12 and a half. And this is purely a categorical thing. I have 12 and a half heads that I expect out of 25. It's just the frequency. And for this one, for tails, I ought to have 12 and a half. These things don't necessarily represent anything. We've pretended like this is coin flips. This is anything where we could have two choices, any kind of binomial setup, so that if we were trying to do 1/4 and 3/4 in something, a probability of success of 1/4, we could do that. So these are just the numbers that come out. So if I want to do a chi-square test on this, the 12 and 13 that I have, or whatever numbers you've got, are the observed values. The 12 and a half and 12 and a half are the expected values. So to do the chi-square test, well, we'll do it the hard way. Pick a spot next to something, and everything I've got here is all lined up. It doesn't need to be lined up. These can be on different pages, different files even. Here I want equals and a paren, and then the observed, which I have 12, minus the expected. Squared. Divided by the expected value. That's the official chi-square calculation. Observed minus expected squared, so it's always positive, divided by the expected values. Right. What this becomes, and it's a formula, but it has a logic. Suppose I'm supposed to get 12, or I observe 12, and I'm expecting 12 and a half. I square it, then divide it by 12 and a half. The top part is the difference squared, and the bottom is the expected. So that in a way I'm doing 1 minus 12 over 12 and a half squared. So it's a deviation from a particular standard. So it's not just a random formula. It's got a reason. And if you can remember the reason, it helps, but it's not necessary. So we got observed minus expected here. And I'm going to copy it down. All right, so now I need the chi-square value. I've got 0.02 and 0.02, and I add those up. And the chi-square test value is 0.04. Does this have a chance of being significant? This one doesn't. It's 12 and 13. It's dead in there. But if I look up the significance, this is equals chi, and we want chi-square dist right tail. We have a value of a chi-square test, and we want the probability in the right-hand tail. Chi-square always uses the right-hand tail. The statistic is always positive. You remember how many degrees of freedom? 1 degree of freedom. We've got 2 categories. We have 2 minus 1, 1 degree of freedom. And this is where the actual p-value, this is 0.84 for mine. So I do the chi-square. Looks like this. Here is 0.04. The area in the tail, in the right tail, is 84%. I'm nowhere near a rejection region. What did you get on yours with 12 or 8, 17 and 8?
I got, for the p-value, I got 0.07.
So yours, what was the chi-square test value? And that tail area is 0.07 something. I'm going to go to another sheet, and we're going to roll dice. So just make a list, 1, 2, 3, 4, 5, 6. We just need the value for the dice that we're going to roll. We want to simulate rolling dice, and we used to do this with real dice, and it took forever because to get a significant amount of them, you got to roll a lot of dice. So this is easier. What command do I want to get 1 through 6 randomly out of Excel? Rand between. This is equals rand between, and we want 1 through 6. What should be the expected? Here I'm going to take these numbers, copy them over, so I have a list. How often should I get an expected value for each of these? They're equally likely. I've got 1 through 6. If I do this 24 times, how many would I expect to have ones? 3. 4. 6 times 4. All right, I'm going to do 24 here, and this is so I can count them. And I don't know what 24 is going to be, so I'll just put it in there. Fill, series, 1, and I got almost 24. I don't know how that came about. So these are my, whoop.
That's the rand between.
Yeah, that's the rand between thing. Yeah, that one's weird. Thank you. Looked good. Had a number. These are my roles. Now, next to here, I want the rand between. Rand between 1 and 6. And then copy that down. So now I have 6s, 2s, 5, 2, 2, 1, 4, and so on. I want to know, is this a regular distribution of throws? And to keep it from changing, I'm going to copy the values, move over 1, and paste the values in those cells. Paste values. Now, the one that's random will change. The one that is pasted values will not. I actually don't need the random numbers anymore. I'm going to blitz those and move this over 1. Let's do the frequency command. Here's my bins, 1, 2, 3, 4, 5, 6, and I want equals frequency. This is the short way to do the histogram. Frequency, the data array is my list of 1 through 6s, random. And the bins are 1, 2, 3, 4, 5, 6. If I do this as a histogram, I want a chart, I want a histogram. What would it look like if everything was the way it was supposed to be, equally likely? Each one would be 4. They aren't 4. But I want to know, is this different than 4 of each? All right, there's my observed values. How many should I expect? Out of 24, how many 1s? Be 4 2s, so on down the line. So here's the observed column and the expected column. We're going to calculate the observed minus expected divided by the expected, observed minus expected squared. So here's going to be the calculation. Equals, put in a paren, 4 there, minus the expected value of 4, squared, divided by the expected value. So it's observed minus expected over expected. Right? In any kind of calculation for the difference between an observed value and an expected value, the calculation is always the observed minus the expected. In this case, it doesn't matter because it's squared. But when you do residuals for a regression or anything else, it's observed minus expected. These are actually residuals. I'm going to copy that down and then add them up. And I can use the automatic add them up. So my chi-square value is 3.5. That's the test statistic. And I'm testing for agreement, basically. Do these values correspond to these sufficiently to say that they work? I got the chi-square value. How many degrees of freedom? How many choices do we have, basically? 6 choices. We always lose a degree of freedom because we estimated an average. So there's 5 degrees of freedom. So here equals chi, and I want chi.dist.right tail, RT. There's the statistic and 5 degrees of freedom. And I have a p-value, a tail value of 0.62. That's nowhere near any kind of significance. I'm back here with this. My chi-square value is here, 3.5, and this right-hand tail is 0.62. So I'm nowhere near significance for this particular test. One last time, go back to your observed and expected, and we're going to calculate the chi-square test value using the function. This is the way you would actually do it. I calculated observed minus expected squared divided by expected and added them up, and I got 3.5. The significance was 0.62. Now I'm going to do the equals chi square test. Chi sq.test. Here's the actual range and the expected range. How does your answer look compared to the one we got from the actual calculations? Here I got 3.5 and the area in the tail was 0.623. That value matches that value. The chi-square test function gives you the probability directly. Doesn't give you the chi-square value. Right, to recover the chi-square value, you have to go backwards. Chi-square. Now I want inverse right tail. You always use the right-hand tail for a chi-square. So I've got 0.623. Number of degrees of freedom is 5. And I've recovered the chi-square statistic. So you can do it using the functions, but if you want to know the actual chi-square statistic, you have to go backwards from your result.